The broadcast is now starting. All attendees are in listen-only mode.
We'll continue, guys, from compression technique, codec operations of MapReduce. The multiple cases we have seen of task failure, node failure, when my task is taking more time to process. How do we manage them, right? Using resource manager, which we are keeping inside Yarn as a yet another resource manager. So we have seen there two services mainly: resource manager and node manager, to handle our MapReduce operation and process them parallelly using slave machines. Now we'll see some other techniques of compression, decompression, counters, distributed cache, a few pending parts of MapReduce. We have seen IntelliJ also. I'm just recapping things which we have covered in last few classes. Using IntelliJ, we have created our jar file. Then we know how to use the jar file, how to submit from client, and that client can be your master or it can be edge node also. Now MapReduce provides you one codec operation. Codec is a package well, okay, which stands for compression and decompression. So the CO part stands for compression, and DEC part stands for decompression. So if I want to compress my data, right? And why do we compress our data? Simple two reasons. One, to make data transfer more faster and reduce the spaces. This is two main reason where we apply this compression logic or mechanism. Now Hadoop supports 6 different compression technique, and the best part, you're not writing any code to achieve this compression and decompression. Hadoop has already provided you the packages for this. I'll show you that in the book, orally definitive guide, after learning basics of compressions and decompression. So starting from ZZ, this is very common one. We know gunzip format. To compress this, we use zip and then file name. So we'll see .zz with the extension of file. Then if I want to unzip it, I can say unzip in my file name, where my file will be unzipped. Now second is a bzip2. Bzip2 is another format. Snappy, deflat, then LZO and LZ4. These are 6 different compression techniques. Let me open actually a book and then we can interact. So it's in chapter number 5. Okay, you can directly go to this. And these are my compression techniques. If you see it, total 6 different compression we have. Now by default, Hadoop uses snappy compression technique. By default, Hadoop uses snappy. So we'll get extension. I'll tell you which one is good in compression and decompression. Well, this is more into the theoretical topic, so I'll try to cover the more main aspect here. Okay, then if you want to read and deep dive into more, you can read this page and chapter number 5. So Snappy is a by default compression technique here in Hadoop, and here we use 2 flag, -1 and -9. -1 -1, as I should call this as -1 and -9. -1 is for speed, if you want to achieve a speed, and -9 is for space. There's 2 different flags we'll be using whenever we compare. Let's say I have a file, okay? Let me put put it this way. Suppose I have a file stored in HDFS, or I'm storing my data in HDFS while migration using some ETL tool. So this data, once this data is stored in HDFS, and I'm listing them using my command HDFS DFS -ls and slash. Okay, so this file will look like this test.snappy. If I'm using snappy format, test.zz conzip format, and same concept, same extensions for other as in this name will also have the extension like this dot deflat dot lzo dot lz4 dot basic2. Now which one is good in compression and which one is good in decompression, as in which one is best compression technique here and which one is a best decompression technique here? So it depends whether you are compressing row wise, column wise. Okay, so by default we'll be using this one. I have personally experienced Snappy is fast for space thing. So Snappy is fast for space. If I want to achieve more space, Snappy can give me the a better hard disk space. So suppose I have a gbzip file and I need to know how many times it is compressing. How many times? Is it 1x time, 2x time, 3x time, 4x time? Okay, so Snappy compression is way faster than others based on the space I'm saying again. So let's read a couple of paragraph here. What this is saying, this is the way you use a compression. So zzip -1 and then your file name. So this -1 is a flag for to achieve this speed, and -9 is for space. This is written here, guys. -1 means optimize for speed, -9 means optimize for space. And we can directly jump here in this paragraph now. Bzip2 decompression speed is faster. Okay, so if you want to decompress something, bzip2 decompression speed is faster than its compression speed. So you can conclude this way that bzip2 is more better in decompression, not good in compression, but it is still slower than the other formats lzo, lz4 and snappy. So bzip is less better than lzo, lz4 and snappy. This is one observation. Now all optimize for speed and are around on, I'm just reading this, okay, for you. And whenever it is required, I'll explain you. Then zzip, but compress less effectively. Snappy and lz4 are also significantly faster than lzo for decompression. That's what I was talking about. Snappy and lz4 are also significantly faster. So Snappy I use personally, okay, for compression and decompression. Now, if I want to achieve any space for data, then how do I write a code, or do I need to import any library to use this? So Codec is doing that on behalf of you already. Codec is a package, and in my property file, in my configuration property file, I just need to add this compression format type and their packages. I need to add this value. So I'll put this value. Suppose I want to use Snappy. For Snappy, I will use this package. Import, I'll just have to write here import org.apache.hadoop.io.compress.snappy codec. If I'm using this import while writing the classes or in my configuration file, then automatically my file will be compressed. So two question can be asked, or two logic is important here. Which one is good in compression? Which one is good in decompression? And how can you achieve it? What is the meaning of -1? What is the meaning of -9? This is about compression and decompression. So go through of it, okay? I don't want to read and bore you reading all this theoretical things. So spend some time here, read by yourself. Still, if you do not understand anything, you're open to discuss. After codec, there's a counters. Second part is the counters. So always we should know first why we are using it, why counters are required. So counters, we have multiple. We have 6 to 7 counters. I'll name them right here. And counters we are using mainly for two things. Okay, first, counters are created only when your jobs are successfully completed. So let me write it here. Counters will only be generated, or will be generated only when job gets successfully completed. So if your job is stucking or failing in between, okay, while processing the task, or in between of node failure, so your counter will not be generated. Counter is the case only when the job is successfully completed, which we can see using application master. It's a part of resource manager. Port number we already know, right? Now, counters we're doing for two things. First, I need to troubleshoot my job for troubleshoot, okay, and there are total insights I want to see. Insights of job. Insights of job means I want to see how many bytes in, bytes out, network in, network out, uh, data written in disk, data read in disk, all this information from map task and reduce task. If I want to understand, I need to know this counters. And there are total 6 different counters. Starting from first is a job counter. So all job related information will get in bytes. Okay, that bytes is the basic type of system. They store all this information in a binary form of bytes. Okay, and we bitwise thing I will tell you just after this, how system reads that information. Now job counter, this is one section where I can see all my job related information. Then task counter, then user defined Java counter. So this is for user defined Java counters. Okay, since my Hadoop framework is written in core Java, that's why internally they are creating me one. They're compiling all these things using JVM. So there is one counter related to UDJ. There's a dynamic counter. There is a retrieving counters. There's a file system input counter, file system input counter, and last one is a file system output counter. So total 7 different counters type we have in Hadoop, which is helping us to troubleshoot and diagnose. Okay, so troubleshoot or diagnose, if I say both are kind of same thing, diagnostic my job uh, after completion. So let's say today I submitted a job. Today I submitted one job, and this job took me. This is a daily job. This is a daily job. Their data types is daily. Every day I submit. Every business days I submit. So business days, when I say in a month total we have 22 days. So 22 times this job is running on daily basis. So uh, today 25th April, right? Today I submitted a job, and this took me total let's say 25 minutes to complete. And they took 4 CPU. They occupy 4 CPU to process it, and they're writing this whole output in some disk, some number of disks, which is based on the data volume. Now next day, when again I'm submitting the same job, which is 26th April. So let's say this job I have submitted today, which is 25th April. So I'm just putting this time to get a clear statistics. If I'm submitting the same job tomorrow, which is 26th April, right? But obviously data will change on daily basis. So tomorrow data will be different, but not drastic change we'll see in a volume. But this job is taking the same job I'm submitting. Okay. This is taking me to complete This time now roughly 49 minutes. So 98x time this is increasing. Now I need to know, when earlier the same job was taking 25 minutes, now it is taking 49 minutes. So what is the main factor here? Is my data increasing? Is my data actually increasing in this date, 26th April? More number of customer are coming. Let's say I'm talking about one job which is a transaction related job, all customer transactions. Okay, I'm checking their opening balance, closing balance, transaction ID, customer ID, their name, their city, and x things, many things we have. So if I'm checking this two factor, and first I analyze that volume is same. First I analyze, my observation is as follows. I think there's a question. Let me put it this way first. I'll complete the part of counter. I'll see the question then. First observation, guys. Okay. Let me start from here again. So I have a daily job, which is transaction related job. This job I submitted today, 25th April at 12 IST. And this is taking me total 25 minutes to complete, and this is occupying 4 CPU and some disk. Now the same job again I'm submitting tomorrow, which is taking 49 minutes. Now using this counter, I will check what is my volume, what is total data volume, both the day, 25th April and 26th April. Okay. If I do not see any difference in this, then immediately I'll check second thing, which is occupied CPU uh, or processed CPU, occupied CPU for task of 25th April job and 26th April job. I'll check, do I have enough number of CPU available in both the date? So is this a reason? Now, obviously, we'll have two reasons. Maybe the volume is increasing, or maybe the CPU is increasing. CPU is less available in my system. Hence, my job is taking more time, because we know that if you submit a job, if you submit this job using Hadoop jar, you say Hadoop jar name. We have created, guys, right? Uh, if you have checked the last session video, we know how to create the jar file, and using some FTP software, which will do when we start the practical of it. After moving this jar file into server where my Hadoop is running, I'll have to provide my class name. If there is a package name, you can say package.class name, then input and output. This is what we do when we submit it, right? Now, the moment I submit, it will give me one job ID. Let me use some random timestamp, 8957243 1 underscore 001. This is my job, and based on the data volume, it starts creating the task. So let me create total 4 tasks. Okay, so when 4 tasks is there, and number of CPUs not available, what we know that this goes to queue, and there's a queue time defined in a scheduler, and we have total 3 schedulers in Hadoop: pair, FIFO, and capacity. And we know all those concepts of scheduler also. So when this is going to queue, it will wait for some time, and obviously when the task is waiting, one case I'll say all 4 core are free. So 4 tasks submitted at one shot, all with 4 core, and it is taking X time to complete the task. But if I have only 2 core available, so T1, T2 will submit, this T3 and T4 will be in pending state. So obviously my job time will be more. This two thing is major reason uh, of your delaying jobs or task. And this diagnosis or troubleshooting, I can check with the help of counters, but only in the case when this is successfully submitted. If it is failing in between, then I need to check the log file. So look, from developer perspective, it's good that you know how to write the code, how to optimize, how to tune it, but you should know how to read the log file also. Because if you're unable to read the log file, you cannot encounter things. And if you're unable to encounter things, then again goes with the process part. How will you write the incident if this thing is not clear to you? So reading log, reading counters, checking system log, checking user logs, checking uh, number of available resources, monitoring things is very important here, not just a submission of job. Uh, Hatim, is it fine now? Are you guys facing any problem? Because I received one message from a guy saying a screen is hanged on blank page. How about you? I can see 7 people are joined this session. Everybody can see my screen, guys, and am I audible? Okay. Thank you. Perfect. So this is mainly about counters and codec operations. Okay. Anyways, Hatim, if you have missed anything, this session will be shared. And we started uploading all this video on LMS section of Poverty. So within a week, I'm hoping that you all get access, and then I will not send you this this files in Google Drive. You can directly log in using your credentials to the site and access this video from there. So let's see. Maybe uh, for next week it should be done. After these two things, um, after these two things, next part is a distributed cache. So distributed cache is providing you one small hack here uh, for the case when my one file is very big and second file is comparatively smaller than the bigger file. I do not have any explanation or the exact number that this is the big file or this is a small file. And there's no fixed number defined. Logically, you need to understand this. Okay. So distributed cache we are using for two cases. This concept we are using for two cases. Case number one is map site join. Map site join. And second one is a reduce site join. Same thing is implemented in Hive also, warehouse management. Okay. So Hive will be our third or fourth module as we go forward in this course. After this, we'll see data extraction. After data extraction, we'll see data processing using a scripting language. So this MapReduce is a programming language, right? People who are not comfortable with programming, there's another option which Hadoop has given you to write a script, handle them or automate them using cell scripting, okay, and then submit it using a scripting language that's Pig, by the way, PIG. It's designed by Yahoo, and currently it's all open source. So big file and a small file I'm talking about, right? What is a big file and how we can use this distributed cache? If you read the title itself, we have one term here called cache. What do we mean by whenever cache comes, immediately you start thinking about RAM, okay? But now you're surprised that uh, MapReduce is doing all the operation, all the mapping operation in CPU and writing mapper output in intermediate location, which is my local file system. They're not writing in RAM. This is why MapReduce is getting slower, okay, compared to Spark. But how this distributed cache thing is working only with some cases, not with all cases. So let's say I have a file with a size 10 GB. One file is a 10 GB, and this can be text data, this can be log file, this can be audio information. Recently, we were processing a VPN log file, so virtual private network log file. Okay, so let's say this 10 GB file is some kind of data, and do not worry with this data because Hadoop can handle any input format. Hadoop can handle any types of data. So I can store it, this 10 GB data, and a small file is, let's say, this is somewhere 900 MB. So I want to do some joining operation within this file, big file and a small file. So I want to do some joining operation. I want to get some common record from this 10 GB and this 900 MB. Let's say this record I have collected from weather station. I've collected this from weather station and I want to aggregate some of the records. So when I say joining, this is the same joining concept. I'm using a SQL, structured query language. There we have inner join, outer join, left join, right join, full join, cross join, self join. I think 7 to 8 types of join is there in SQL. Other than this normal joining, Hadoop is providing you one map site join. But again, remember this small note. When one file is comparatively bigger than another file, then we use distributed cache concept. Distributed cache concept or mechanism to reduce business execution time. First, I will tell you first scenario I'll put for normal operation. Okay, not distributed cache. What normal operation does and how the flow works here. So you have your input file. This is your input, and this input file is stored in HDFS. Let me take a size of this file as this file is having size of 500 MB. I have stored this in HDFS. Okay. Now, how many tasks will it create? 500 MB. So total 128 MB. T1, 128 MB. T2, 128 MB. T3, and last will get 116 MB. That's my T4. I'm using by default block size. So total 4 tasks it will create, and it will create 4 input split. So after input, there is 4 input split, 4 input split, because this is splitting your data in 4 different partitions. Now, what is the input and what is the input split? So block is equal to number of input split. Block is equal to number of input split. So block size is by default 128 MB. So input split will also be 128 MB. But what is the difference if both are same? Block is a physical division. You can see the data, right? We have seen this data after copying it. But input split is an internal process. It's a logical division. To read your data using record reader. So input split is happening inside the node manager, guys. Okay, the moment I start this input split, I submit it immediately. First step is my input split. Input split means my task is now getting submitted into CPU. The moment it gets submitted into CPU, I say my map task is created. Okay, so currently I'm taking example of 500 MB data. So 500 MB data means total 4 tasks. Four block. This is my 4 block, T1, T2, T3, T4. How many input split it will create? 4 input split. And this 4 input split will submit in how many map tasks? So number of mapper will be how many? Number of mapper will be 4. So here I'll say 4 map task. I can customize this, okay, but I'm currently using the by default one. Customization option we already know, and we've tested that using DFS dot in file copying in the multi-node cluster. So 4 input split, 4 block, and 4 map tasks, which means I need total number of available CPU to run my jobs parallel is 4 CPU. This is current statistics. Now, input split will be 4. So this input split will create total number of tasks in mapper. This is a mapper stage. It will create 4. It has 4 input split. This also has a 4 block. Now, why your MapReduce is taking more time? I'm currently warming up you guys to understand this distributed cache concept. Okay. 4 map task it is creating. Now this map task will start one by one. That T1 is started, T1 is started, then T2 is started with some percentage. Similarly, T3 started and T4 is started. Now there's a question. Uh, when I submit my job using this command, so I see mapper 0% and reducer 0%. This is how it will start. So first mapper will complete, then only reducer will start, or it can be started in between. That configuration again you can put. There are total 3 options: 0, 0.5 and 1. So if it is 0, then your first mapper will complete 100% and then reducer will start. But sometime you'll see while submitting the job that this is 33% done and reducer has also started that 10%. Okay, so this is based on our configuration property. That property I will tell you. We need to fix the threshold. There is one point of threshold which I need to export in my cell or add in the property file. So the option is with us. If you want to complete the map first and then want to start reducer, or if I want to start reducer in between. But I'll suggest once the complete mapper part is done, then reducer starting is more better option compared to completing starting in between. Because what will happen? Suppose you started doing this mapping and reducing parallelly. So total number of map task is 4. T1, T2, T3, T4, and it has completed 40%. This has completed 21%. This is completed 32%, and this is 3%. And these are all my map task. Individually, I can track all of this task using my port number 19888. This is our node manager. Now, suppose you said I want to start reducer, and you fix the reducer task. And when we write a code for MapReduce, we can actually set this number also. So 1 can be taken by default, or we can set this number also. I can say that I only need 2 map tasks, or I need 3 map tasks. How do you know this number? You need to check the capacity of your cluster, that how many total cores are free, and based on that define this. Now suppose I'm giving 2 reduce tasks, T1 and T2, in my MapReduce code. So T1 and T2, if this is started working after this, since my property of threshold is set as 0.5. Okay. Now this is started 10%. T1, the moment this T1 process 60%. Okay, the moment this T1 process 60%. So now this T1 is taking input from this also, this also, this also, and this also. If it is aggregating some of the tasks, because reducer is doing what? Reducer is for aggregation. Mapper is for transformation. Reducer is for aggregation. So if this T1 is needing all output, okay, all output which reducer wants to produce, the input is T1, T2, T3, T4. It is aggregating from all of this task, and continuously this process is going. So performance may be slow down. Okay, if it is needing input from all of this. So first, my recommendation for you guys, first complete the map task and then start the reduce task. If you start in between this, then it is taking this input file, this input file, this input file, and aggregating the output in T1 and T2. So output I'll get it. I'll not get any error or exception, but performance maybe slow down here. So how can we handle this part? Here, 4 map task is there, T1, T2, T3, T4, and where this output will store, guys. So when individual mapper is done, when my first task is completed 100%, when my second task is also completed 100%, or whatever spilling is there, okay, you see this point, mapper 33%, reducer 10%. This step is known as a spilling. Spilling means 33% of input data have processed. 33% of total input data have processed, which means 500 MB of 33%. Let me calculate it. So 500 MB is my actual data size. We don't have a space. Okay, let me here. 500 into 33%. So this will give me roughly 165 MB of data it has processed. Okay, that's what is the calculation of 500 MB of 33%. So total 165 MB data will be spilled, but where? Mapper output will go in HDFS or mapper output will go in local. So mapper output is going in intermediate location. Mapper output is going in intermediate location. And intermediate location is my local file system. Remember this point. My map task output is not getting stored in HDFS. My map task output is getting stored in intermediate location, which is my local file system. It does not cache it. There's no caching concept. That's the reason they take more time if I start reducer. So I'll use partitioner, I'll use suppling sorting. Suppling sorting stays the reducer stage only. And then I'll start aggregating my output. Reduce. I'll take one example after this, okay? How this whole process will work. Map task, partitioner, shuffle sort, and reducer. Now question is here, this reducer is having reduced task, the number which I have defined. Now this reduce task will read this input, from where? From local. This is what makes my system or process slower. In Spark, this does not happen by default. In Spark, whatever output is processing in this side is not getting stored in your local file system. This is getting stored in your RAM for caching operation. Okay, so we already know that what is the main difference between MR and Spark, that one is a disk computation model and second is an in-memory execution. Now looking at this whole picture, I can make one statement that writing output in disk and writing intermediate output in RAM, which one is more faster? Obviously this caching is more faster, and that is the reason why I'm doing this concept. That is the reason why I'm working with the distributed cache, but only in the scenario when I have one file comparatively bigger than the other one. Then I'll only apply distributed caches. What this distributed cache will do, it will store this small file. It will store this small file in cache. So we need to add one property, okay, and define the size of it. So we need to add one property and define the size. So this 900 MB data will be actually cached in my RAM. Now when I am processing reducer, okay, when I'm doing reducer, so now this reducer is not reading from local because my small file is stored in cache. So this RAM can immediately pick this reduced task can pick this file from this RAM and perform the caching way faster than the disk operation. So this is just to enhance the performance. They have given you the concept of a distributed cache for a condition of big file and a small file. This number I have just taken for example, not necessary that you have 110 GB or 900 MB. Maybe I have 100 GB one big file and 2 GB as a small file. So I should have RAM available of this much, then only I can cache it. If there is no RAM available of 2 GB, then how can you cache it, right? This a small file should be fit in this cache. If you have cache of 1 GB, okay, your system configuration is very low and your file is 2 GB and you're thinking that can I use a distributed cache concept? No, absolutely no, because your RAM size is 1 GB only. So we should check this first. What is the total cache available? What is my small file? And then if both scenarios are fitting with my application, then I can start with this approach. So how the mapper task and reducer task is working. Uh, Suppose I have a book to read. Okay. Suppose I have a book to read in Hadoop. And my task is, so this is my task. I have a book. We have a book of 500 pages. Let me take 700 pages. We have a book of 700 pages and want to count want to count how many times how many times okay how many times Hadoop is written. Hadoop as a word is written, and Scala is written. Hadoop and Scala is written in this 700 pages. So task is to count that out of this 700 page, how many times we have this word and how many times we have this word, Scala word. So I don't want to use first MapReduce. I want to build my analogy. I want to build my concept first. Then I'll start following this process, input split and all. So since we have currently 7 people here, okay, what I'll do, I will, the problem is this. So this is the task and currently I'm not distributing among you guys. I'm trying to solve this problem by myself. So me as one person reading this whole book of 700 pages and taking total 300 minutes, which is roughly 5 hours. Okay, so 300 minutes I'm taking to count this Hadoop and Scala word, and after 300 minutes I'm able to comment that Hadoop is total 16 time, okay, and Scala is total 27 time. After 300 minutes I'm consuming, okay, and then I'm saying this time maybe I'm using my manual approach, I'm writing some script, okay, or I'm reading one by one, but the time is this. Now business says that I want to increase the performance. So currently this this is not a distributed computing or parallel operation. This is just one person. So one person means it's a kind of sequential concept. And I decided to distribute this whole task of 700 pages to you guys. So I said I pick up 7 people. I said P1, P2, P3. Let me take this in new page. We have P1, P2, P3, P4, P5, P6, P7. This is total 7 people. Okay. I've given all of them how many pages? 700 pages divided by 7 people. So all will get 100 pages individually. all will get first 100 pages equally, because I'm distributing all the tasks equally. That's what is the best computing. Because if I give anyone 500 pages and other person 100 pages, my resource is not properly utilized. So I want to utilize my resources well, and hence I'm doing this. So after distribution of this 100 pages, they start working parallelly, right? Because they're not communicating to each other. They're not sitting in the same location and then saying, okay, how many you have done, how many I have done. This is all co-located, maybe in different server, different region, different machine, okay, different CPUs definitely. So P1 is completing. Earlier it was taking how many time? 300 minutes by one person. So simple math. If 7 person is there, how many time? 300 divided by 7, which will get me 7 into 4 is 28. Then 2, 2, 6.8, and 5. This is the total minute for 7 person now. So almost I have 7x time my performance increased. But how? This took same time. 42.85 minute is taken by all people, P1 to P7. In the side me, okay. So I have total Hadoop H. I'll represent Hadoop as H and Scala as S. H, S, H, S. HS and another HS. Okay. This person says first, I do not get any Hadoop. Hadoop is there 0, but Scala I found total 3. Then this person says, I have total 3 times. This person says Scala I found total 0 time. This is now this 1. This also 1. This person says I get this 7 times, and Scala total 4 times. This 2 times, then this total 5 times. So 7 plus 3, 11, 13. This is 2, this is 1, let's say. And this is total 5, 4, 10, 13, and 27 is right. So 1 is getting 10 times and 4 times. So this is their individual performance. They all total time they have taken 42.85 minute 85 minute to complete the task, but individually, right? If I add this Hadoop 3 plus 1 plus this is total 11 plus 5 16, that's what was requirement 16, and the Scala is 27 3 8 18 and 9 27. Now what I'm doing currently is this process is nothing but a map base. This is how your mapper works individually. They occupy one CPU, okay, and based on their data availability, data locality, they start processing, and they're individually processing. Once this P1 to P7 is done, now somebody has assigned this task to these people. So there's a master, okay, there's a master who has given this task to all these folks, all these people. And one more time, all these people. The task is given. Now once this is done, how do I know they have completed the task successfully or not? So obviously they are acknowledging me back individually. Yes, we have completed this task. All acknowledgement will go from P1 to P7 to master. And this master is nothing but your resource manager. And this process where this whole thing is happening is your node manager. Once this is done, then reduce task time, the time of aggregation. Okay, the time of aggregation. And guys, I'm writing this 7. Okay, I'm writing this 7 and 4, but actually the internal logic is this. Internal logic, they do not aggregate here. They write it as 1 1 1 1. They do not aggregate it. They write in a different data packets. So if there is 7, okay, I should not aggregate this since there is no space. That's why I have written 7. But you understand internal approach of map task. This is not aggregation here. It's 1 comma 1 comma 1 comma 7 times. Similarly, 2 times here, 5 times here. So I should not write or aggregate it here. Just like this, I will write for all. This is a mapper. Once they acknowledge back to master, okay, the master will say, now I need to run reduce phase, which is my second phase. Now how this reduce phase will start? Again, master is there. So master will say how many times we have, where we have more input for Scala and where we have more input for Hadoop. Because I will send all this information to this. Because sending this 7 packet to all this individual machine would take more time. Instead of doing this, what I will do, I will start communicating from this P1 to P1 to P4, P2 to P4, P3 to P4, P5 to P4, P6 to P4, P7 to P4 for Hadoop thing. Because maximum h equal to 7 you have here, 7 times 1, 1 comma 1 comma 1. And similarly, you have 10 times Scala here. So for Scala aggregation, all this machine will communicate to this one by one. And this communication step is known as a shuffling part. So we shuffle this data based on network packet where we have more input available. Okay, and who is deciding Hadoop will go to P4 and Scala will aggregate in P6? So one thing is clear, that to avoid our network traffic time, we are selecting one machine where my Hadoop number is more. I'm selecting one machine where my Scala number is more, and then all this other machine are communicating to this two machine. All this other machine are communicating to this two machine. So H thing and S thing is taken care by this thing, partitioner. Who is deciding that Hadoop will go to which machine and Scala will go to which machine? This is a job of partitioner. This shorts the key. This shorts your key. And once the key is sorted, they start shuffling it. This is the time taking operation. Your most of the time of MapReduce process will be actually taken by this shuffling sorting. Because in shuffling sorting, what exactly I'm doing, I'm communicating. Let me represent this whole picture with number of machine. So I have total. So this is my input file. This input is nothing but my 700 pages of book. Okay, and 700 pages of book I am distributing in total. How many input is split? 7 input is split. Because I'm defining this to 7 people. So 1, 2, 3, 4, 5, 7. This is my first input is split. Input split. This is my second input split, third, fourth, fifth, sixth, and seventh. Here I have 100 pages. Okay, now map task started for this. So map task will count how many times Hadoop is there. H equal to 0. s equal to, if there is 2, it will say 1 comma 1. That's what I'm talking about. This aggregation will happen in few cases only. That case I will tell you, but currently I'm not aggregating in my mapper. Currently I'm not aggregating in this mapper. And similarly we have Hadoop 1 comma 1 is equal to just 1. Like that we have Hadoop and Scala processed here in individual map task, which are processing in separate CPU and uh, separate node managers. Okay, who will decide this? That H and S key will go and process in which machine? This is a partitioner job. This is a partitioner job. Partitioner does that, and shuffling sorting will start. So suppose I have total H here, Hadoop here. Hadoop is how many times? 16 times, right? So here Hadoop will come 1 comma 1 comma 1 comma 1 until 16 times I will have this Hadoop. 16 times I will have this Hadoop. Then similarly, this is processing in one task. Similarly, I have Scala is equal to 1 comma 1 comma, and this is total 27 times. So to do this activity, all this machine are communicating. All this machine are communicating wherever I have this Hadoop key available, and Hadoop key is available in all the machine, right? This step is known as a shuffling and sorting. And what I'm currently doing is my shuffling phase. Once this is shuffled, then reducer, I'll continue from here. Then reducer will say H equal to 16 in one disk and S is equal to 27 in another disk. And then final output, I will get in a file where I have this result stored. This is what is internal operation. Now, if I'm having 1 comma 1 like this, I have 3 times Hadoop here, 1 times Hadoop here, 7 times Hadoop here, similarly 2 times, 2 times, and 1 times. If I'm sending this packet, this communication is sending one packet at a time. One packet at a time using ICMP protocol, Internet Control Message Protocol, just like the way you communicate from your machine to some application server or some cloud. So you receive some message from there. If you're receiving message, which means there is a ICMP protocol enabled. So any data transfer or network packet transfer happens based on this port number. This is a protocol. So one packet at a time. Now if I have 3 times Hadoop retain, which means I am first communicating, so first I'm sending the data to one reduced task. Then this is acknowledging me back, yes, this is done. This is what happened, right? Otherwise, how do you know that the communication is successfully done or not? Like if I'm communicating to you guys and I'm asking you some question, but you're not as in I'm asking you that whether you're able to hear me, you're not responding me, I don't know. The communication is happening here or not. So the same way, this one data one data packet has transferred from this machine to this machine. This is a request or send, and this is acknowledgement. Similarly, it is happening 3 times. If I have 3 times that key available in your reduced task. So isn't it this is a time taking operation? Because if I'm sending the same key 3 times and one key is taking 0.13 second, one data transfer rate is 0.13 second. I'm just assuming it, okay? 0.13 second based on my CPU. So 0.13 into 3, this many times it will occupy for just one machine, 0.39 second. How can I enhance this operation? How can I optimize this? So to optimize this, there is another approach, and that approach is known as a combiner. Look guys, in MapReduce there are many concepts. Okay, so that's what I said. From chapter number fifth to ninth, all thing is written about MapReduce, and whatever processing we are discussing and we are yet to discuss in a scope, in Hive, in HBase, I'll be using these references. Okay, please mark my word. Go through all of this video, whatever we are discussing in MapReduce. I'll be referring this whole concept in Hive, in a scope. Wherever MapReduce will come as an execution engine, when wherever MapReduce will come as an execution engine, I'll be using this concept. So if you have anything, any doubt, okay, we are open to discuss today. Combiner, let me first complete, but combiner, what combiner is doing? Combiner is known as a mini reducer. So I can call it is a mini reducer. It is a mini reducer. And I will share this all the PPTs and today all the docs with you. Okay? So you can start referring this concept as in theory part. It is a mini reducer. So what do we mean by mini reducer? It is doing local level of aggregation. So combiner is again fitting in few cases, not in all the cases. And combiner is reducing my transfer time. Combiner is working as a mini reducer and it is reducing my transfer time. How? So combiner can do this job. You're seeing currently that this is 3 instead of 1 comma 1 comma 1. This is 2 instead of 1 comma 1. This is 3 instead of 1 comma 1 comma 1. Similarly for all. Okay. 5 and the more time 6 1 1 1 1. Any more left? 1 comma 1. This is 7 times. That's it. Okay. So instead of sending this packet one by one, what combiner does, combiner will actually aggregate it here in local machine itself. In your mapper task here itself, in this mapper task here in this operation, your combiner will aggregate it locally. They're not aggregating from this machine and they're communicating to this machine. This is not happening, guys. They're not communicating from one to another machine. They're just aggregating the local machine input file. So if each I have 111 written multiple time and sending this packet one by one, combiner will say why you are wasting your time and traffic. I'll do one thing. I will aggregate this and say S is not 1 1, this is 2 actually. And how this is helping me? So earlier it was taking 0.13 second 3 times data transfer rate is 0.13 into 3. Now I'm just sending this data one time. So 0.13 second and I transferred all this three packet. So this is just a very micro information, but what if you're processing millions of data? What if you're processing millions of rows and TBs of data? This can actually get you the bigger number and bigger time enhancement. Okay, so scalability we can do where we have many options for scale up our program. We can scale up in the input split side. We can scale up using customize of input. We can scale up using combiner concept. We can scale up using number of map tasks, increasing and decreasing. We can scale up using reduce task operation. Okay, so it's not you write one program and then you submitted one program and you get the answer. Your program, no, none of the programming works in this way. We always do trial and error. So first we write the program, we test it. Uh, let me talk from the developer perspective. Okay, so these are the aspect. First, I read problem statement based on the application. I read problem statement that what is the problem. Then I build a solution. Build solution. Now once the solution is built, I start testing all the use cases. Testing use cases or their functions. once this is tested, then I'll see my total time, uh, total execution time. Then I'll try to tune the time based on my function. So this step number 2 and step number 3 is a recurring business. Every day you are doing this. Every day you are checking the cases, you are optimizing the functions, you are checking the time. So let's say today this is taking total time 60 minutes to complete something. Then you'll see, why don't I complete this in 50 minutes? Do we have any scale up option? So this is what is known as test and trial. And obviously when you do this, you get bunch of error exceptions, which you handle using exception handling codes. So all coding part I'm not picking right here. Coding things um, I'll be discussing end to end in, sorry, it's a Scala. So end to end I'll be discussing this whole part in Scala. How to handle this all, how to write the test, trial, error, and etc. So this is pretty much your MapReduce. Okay, coding part we'll see when we understand the Scala, and because the same thing will be used in a Spark to write up the code. But before working with MapReduce, Hadoop is built for what? Hadoop is designed for OLAP purpose, right? Online analytical processing. Online analytical processing. So we don't have any real-time data stored in Hadoop. We have all historical or batch data, right? We're extracting from somewhere. Now you say your cluster is ready. Your cluster is built in your firm. You start log in using your credentials, and you can see number of services running. You can monitor them. You can see CPU availability and lot many things. But question is, if this HDFS does not have a data, because HDFS first needs input. We are so far copying one sample input file using this command hdfs dfs minus put, or copy from local and then source and destination. This is the command to copy the data local level. But how in real-time system this HDFS will get the data? This is just for our understanding that this is the command to copy this. But if I have TBs of file, I can't use this one by one operation, right? To do this, you have your upstream source. This upstream source is some website. This upstream source is some website, some web server, flat file locations. Okay, so let's say this upstream source is firm, of some banking firm, and this banking firm is having total 10 years of data. Okay, so 10 years of data. I'll take it in the downstream source. Upstream source banking, and this banking has some website www.xyz.com. This is the website where you go, where you do all your purchasing, your transaction, your withdraw, your credit entry, your portfolio management, many things. All customer management you're doing in this website. Now you guys tell me, this website is hosted in some server. This is hosted in some server, right? With some IP address. Let's say that IP address is 192.168.10.1. Now, using this IP address, can I check my server location? I can check that where this server is hosted. Once I know that this server is hosted at this location, then this entry is directly connected to your downstream source. This is what happened in actual time, guys. Let's say you have any query you're practicing today, at 7 p.m. Okay. Uh, 1 second. This is taking time. Yeah. You visit this site and you're having this query. So when you have any query, okay, I'm trying to actually replicate the scenario. So you have this query box. So when you're practicing anything, you're getting any issues for practice, you fill this form, this name, this email, this contact, this subject, this message at 7 p.m. So we're not expecting anybody sitting immediately and getting response. Right? This goes to queue. This goes to your number of queue. Like total today, 10 people have questions, so this will go to queue. Then from support, somebody will assign it. They will solve the ticket, and they will ask you that if you're satisfied, give us the feedback and XYZ something. Now, I'm more interested to know that when you submit this form and click on this send, where this data is getting stored. So this data is connected. This whole thing is connected with this DNS, which is your domain name server. The same I said xyz.com for banking operation. So this is one DNS, and this DNS is hosted in some IP, and we know the IP address, and we can check the location also. Now this information is getting stored in a form of table in your downstream source, and this downstream source is nothing but my relational database management system. Oracle, SQL, MySQL, Teradata, Ab initio, MicroStrategy, NetAja, PL/SQL, etc. Many tradition boxes we have. Though we are using less today due to NoSQL demand is very high now for low latency data, but still this cannot be completely scrapped. Maybe after 5 to 10 years, we may see some changes in this, but not immediately. Now, RDBMS is having all this information in a form of this entry. So RDBMS is having this entry. RDBMS has created one table already because RDBMS basic concept, if I talk about, this works with the predefined schema. This works with the concept of predefined schema. You'll have to define the schema first, then the entry can happen. So somebody has created the table from the technical team of that website that create table cust. This is a SQL DDL statement. Okay, people who are good with RDBMS, they can understand. People who are seeing this first time, this is the simple data definition language, and I'm writing one SQL terms here. So create table cust, and then I will write name, email, contact, name, which is a varchar or char or string. It's a basically a sequence of character, and I'll fix the range of this. The length is 10. Similarly, email, this is also 10, let's say, and obviously we have data type as varchar. Third, contact, subject, is also 10, and last I guess comment, subject and message. Since message is having list of more, I'll say string. Okay, or I can define large binary or large uh, glob and blob. Those we have also as binary object. Once this is defined, my this information is getting connected with RDBMS and inserted in that table. Inserted in that table the moment you click on the submit. So this will have an entry when I run a query select star from table name, which is my cust. So let's say one person has query. I'll use name. So name is, let's say, Mayur. Email is some gmail@gmail.com. Contact some number, subject is Hadoop, and then your statement written here. Now I want to extract this data which are stored in RDBMS from here to there to analyze it. This is what I was trying to explain here. So all this banking information is holding data like this only. When you transact anything, this is all going stored in your RDBMS. Okay, precisely this is Oracle. Say this Oracle. So from Oracle 13G, I'm extracting this data from here to there. Then only I can start the OLAP part. If data itself is not there, then I cannot start anything. And to extract or migrate this information from this box to this box, we need some ETL tool here, right? Extract, transformation, and loading. ETL is required, extract, transformations, and loading. And we have many ETL tools available to do this today. We have a scoop. We have this scoop topic as a next module. We can do using a Spark SQL. We can do using Informatica. So this is for people. This is important for people who are having 10 plus of experience. That this question you may face: why Scoop? Why not Spark SQL? Because you need to design the class. You need to design the project. You have to design the workflow, the architecture part. So you'll have to compare actually that Scoop versus Informatica, Scoop versus Spark SQL, and see pros and cons. Okay, to answer question based on your experience, because they're not asking you to write the code and all, right? They're expecting some principal architect from you. So principal architect means I need to know that why specifically I'm using a Scoop. Do we have any reason based on the application? Do we have any reason based on the problem statement, or what exactly is the reason? So once I know that point, that yes, the Scoop is fitting best, okay, or Spark SQL is fitting best, then I can choose, I can opt, and I can start extracting this data to HDFS. But one thing to remember, that all this entry in this RDBMS is there in a form of table. HDFS abbreviation is Hadoop Distributed File System. This is not a table now. This is creating me separate files in HDFS. Then modeling, data extraction, data massaging, data warehouse management, data changing capture, data slowly dimension, all that thing we can do later on this HDFS. But my first objective is to get this data into data lake. Okay, so data lake staging layer we use, right? Whenever you see this data lake and staging layer referred as a terminology when you're reading any textbook, this is what? This is HDFS. That extracting all this information, keeping in a centralized repository is known as a data lake or a staging layer. So we used to call this as a staging layer in my banking previous experience. Currently, I'm working mostly into data science application and extracting some real-time data. I'm not more into the historical. So my previous experience is into historical. That's what I'm currently talking about. Now we'll see this extraction part. How Scoop can help me to extract the data. We'll see one by one. Scoop is there, Spark SQL. Informatica is not there in the Hadoop course, guys. This is a separate part altogether. It's a tool, by the way. And using this tool, there are some kind of plugin designed, and they use Informatica boxes, but only in the case when this is Informatica. So we're extracting this data from here to there, then you can use this Informatica plugins. But if this is RDBMS, I'll recommend you to use this too, Scoop or Spark SQL. Let's see the pros and cons. What pros we have there, why this is recommended, for which cases this is recommended, which application this is fitting best. This is my analysis. So Scoop is my data extraction point, and if you see the name, it's a baby of SQL plus Hadoop. It's a combination of SQL and Hadoop. The SQ part is taken and the OOP part is taken and made Scoop. Okay. Now Scoop is extracting data from RDBMS, and this can be any or not specifically Oracle. It can have Oracle, MySQL, PostgreSQL. There are 5 to 6 names. Postgres, MicroStrategy also they started supporting, I believe. So RDBMS, and I need all this data in HDFS. So I want to create a bridge here, right? I want to create a bridge here for communication, and that bridge is created by Scoop. That This bridge is created by Scoop for communication, and this is a utility. This is a one tool, and this tool is this is created by Cloudera, and then later they again donated to Apache for large development and fast processing, okay, and many other enhancement. So this is currently managed by Apache. Everything is managed by this terrific community. Apache. You can also join this community if you want to be a, a nerd and good programmer. Okay, so Scoop is taking this data from RDBMS and writing to HDFS. Now, can we know where this all thing have installed? Where we have HDFS, where we have RDBMS, where we have Scoop. So I'll be using our cluster setup part is done. The basic practice we know. The MapReduce concept we understood how the task is created, how the flow will work. Now we'll see. Uh, Now we'll see how my data can be extracted and in which file format. In which file format, what driver name I'm using, what communication protocol is there. So RDBMS is installed in your Windows currently, right? This is in some Windows machine, or ideally this is in a different server. I can call this is a server. This is in one server, host machine. This HDFS is running in your Cloudera. Now going forward, I'll be using CDH 5.13. CDH 5.13. I'll be using this. This has all the Hadoop software already running. All the Hadoop daemons are already running here in Cloudera. So this makes my job more easier for development perspective. Because if I want to work with a manual, it's good for administrative purpose, but for development, it is headache actually. That if a service is not working, again you need to spend a lot there to check the log file to understand the problem. So I'll be using one ready-made environment because we know now how to create the cluster and all. If you think I want to use GCP or something, you can use that also. You just need to have these 3 services running. That's it. So CDH 5.13 I'll be using. This is a package, and it is installed in a OS called CentOS. CentOS, and this is 6.4. Scoop is also installed in the same machine where I have my Cloudera and HDFS thing available. So let me write this is also CDH 5.13. This is also 5.13 and CentOS 6.4. Can I call this as a different server? This is one server and this is the same server. So let me call this is server 1 and this is server 2. Now, how can you communicate from one operating system to another operating system? Do you need to enable some port or some protocol, or you need to grant privileges? Then the data transfer or network packet transfer can happen, right? Yes, we'll have to do that. So Scoop is a utility, and this utility is written, the tool is written in core Java. So we'll be not writing any application in Java, we'll be using this tool, simple scripting tool. And internally, they need a driver. They need a driver to connect RDBMS with HDFS, and that driver is JDBC. So this is the most common driver which we use here. JDBC abbreviation is Java Database Connectivity. There are total 4 driver guys: JDBC, ODBC, Open Database Connectivity, Native API, and Thin driver. 4 different drivers are there. I'll be using JDBC because the name itself is Java database connectivity, and this tool is written in Java, so it can create a best communication. Okay, and obviously uh, fast transfer. So I need this JDBC driver to be connected with this scoop. So I'll set this scoop part with JDBC first. I'll download the lib file of it, the jar file of it, and push into scoop library. And this scoop library is present in Cloudera. So I'm currently designing the basic architecture, basic flow. Now scoop is requesting, once it gets this JDBC in library of a scoop, and a table is created already in RDBMS. Precisely, this is Oracle, or this is, let's say, MySQL. Any of the database can be there. Okay? So first it will request that, can I communicate to you? Then if I have granted permission in RDBMS, if I have granted permission, so there are a query which we submit. There are a query like grant privileges on star dot star to root at the rate IP address, whatever IP address you want to grant, identified by password, whatever password you have with grant option. This is one query. We'll run this all the query when we start this practical, hopefully tomorrow. So RDBMS is requesting, and RDBMS will give one acknowledgement to scoop that yes, the communication is there. And how do I know the communication is there? Because for this I need to ping. I'll ping the IP address from this Santos machine, IP address of this, because my last objective is to get data in this location in HDFS. So obviously I want to check the communication from this machine of this IP. So I'll be writing ping and IP address of this Windows machine. And again, when I say IP, there are multiple IP, IP4, IP6, MAN, WAN, Ethernet, LAN, many IPs are there. Local network, IP address, IP NAT address. So which IP to take here? IPv4 for sure. And there's one communication which happens with VMNAT1, virtual machine NAT1. So this is one name. Let me show you actually that where I will get that IP. So if I open my terminal, this terminal, same thing. You guys also have machine. You can open your Windows CMD command prompt and type ipconfig there. Windows runs with ipconfig. This is the Unix based OS, so it will have ifconfig. When I run this ifconfig, there are so many IPs, right? There's this one local IP, there's another IP. Then I'm more interested to check where is VMNAT1. Okay, let me open new ifconfig status. Okay, so currently my virtual machine is not open. Okay, look, there will be one VMNAT1 IP. Currently this is not working because I have not opened my VM, my virtual machine. I believe all of you have virtual machine installed in your machine, right? Ubuntu and Cloudera is there. And if you open Ubuntu or Cloudera, any of this, then there will be one new IP come. A new IP address will appear here. And that IP address will appear with the name VMNAT1. There will be one more IP address with the title VMNAT1. Actually, two will be there, VMNAT1 and VMNAT8. These two title will be there, and both title will have some IP address. This will have one IP address, this also will have one IP address. So VM stand for virtual machine network 1. I use this IP address first. If this is not working, I can check the second one for communication purpose. Okay. Now I will ping this machine. I'll ping this IP because currently mine is Unix based. I have MySQL installed in this machine, in my host machine. I will extract all that data from my host machine to my guest machine, which is my Cloudera. Right? This is my host and this is my guest. Because this is running on top of VM, this is running on top of virtual machine, and this is my actual operating system, just like you have your Windows. So if I want to ping this, what I will do, ping and IP address of this machine. So let's say this IP address is 192.172.16.5. If this is IP address, if I'm running this ping command, if I'm running this ping command from here, from this CentOS, and this is giving me, this ping is giving me 64 bytes transfer rate of ICMP packet. That's what I said you, Internet Control Message Protocol will be applied whenever you communicate. So 64 bytes ICMP message if I'm receiving, which means the communication is there. They are eligible, they're allowed to send packet and receive the packet. Both communication can happen. Okay, but if this is not working, if the 64-bit byte message you're not receiving, which means the communication is not stable. Okay, and there can be multiple reasons. Let me list down. So if you guys face, okay, today I'll recommend you, please open, okay, because from tomorrow I'll be starting with my practicals of scoop of data extraction, because before processing any data in MapReduce and in Spark, my job is to get this file. So I need this data extracted right here in HDFS, then I will process it. Then I will process based on my logic of MapReduce, Pig, or Spark. Initially we'll pick this three, but first we need data. And anywhere if you work in any organization as a Hadoop engineer, data engineer, your job will be first to extract the data. If you have any RDBMS available in your server, in your system, that will be the first role and responsibility, not the processing part. So here, if this is not working for people who are opening VM, they're trying to ping their IP address. First error, please check your firewall. If your firewall is on, try to off and again check. If it is not working, please reboot your system. Please reboot your system and again try it. So most of the time that should work. This can solve 70% of errors. Okay. Second problem, if this is not working, maybe port is not enabled. VM port is not enabled. VM port is not enabled. Now to do this, to diagnose this, if you face such issues, please take the screenshot and communicate with me offline. Okay, so, after the session or before the session. So check this VM port, and if this is not enabled, the communication will not work. The third problem, maybe there we have to do one setting from BIOS. So BIOS setting, if your VM itself is not opening, so when you click on the VM and they start giving you unwanted errors, which you're unable to understand that what exactly this error is telling. So do not do anything with BIOS, because if any misconfiguration do in BIOS, your whole system will corrupt. So if you're getting that VM is not opening, don't do anything. Directly come back to me, and I'll see your problem. So this three problem can be listed. Check this today. If you're getting 64 byte, no need to do anything. Your communication is stable. You can start directly working with the practicals. If this is not working, then These three diagnoses you can perform from your end and observe the error. Fine, guys. So this is how communication, then scoop, then HDFS. Now scoop argument. Okay, and literally this is the terrific tool. It can get me one table at a time. It can get me thousand of table at a time. It can get me few columns at a time. It can encrypt the record. It can compress them. It can serialize them. It can use the file format. It can put the boundary condition. It can run the simultaneously job. Okay, so many operations we can do using this tool, which is scoop. Number of arguments which are there. Scoop arguments. Okay, scoop arguments we have total 6. Import. This import is my daily argument. Like I'm submitting this every day. So if I want to take one table at a time, and the communication happening, this communication is happening from RDBMS to HDFS using a scoop. So one thing is clear, that scoop is requesting to RDBMS and getting the acknowledgement. But after that, scoop will extract the data from RDBMS and store in HDFS, which is your import call, which is your import call. This is what will happen when we start with it. So import is doing this RDBMS to HDFS, one table at a time. Okay, you can put conditions on that table that you need this boundary query, you need this many column. Suppose you have 1,000 rows, you can say I need 100 rows. Suppose you have 10 columns, you can say I need 2 columns. That manipulation you can do as per your requirement. Now second thing, after import, so obviously if I want to import multiple tables at a time, there is argument import all tables. Import all tables. And import all tables will extract you all the table from one database to HDFS. Okay, one database. Database, when I say I can create ORG as a database and keep 5 tables there. So if I need 5 tables from RDBMS to HDFS can be extracted, I can do that. Second, what if I don't want all the table? Maybe I just need 2 table out of 5 table. I can exclude 3 other table which I don't want. I can also do that. Can I do vice versa? Practically, I have never used this because my business has been sensitive since beginning. But maybe if you're working in a travel industries or maybe in logistic firms or real estate company, export operation can be there. In our firms, in my business domain, this was the data breach policy. So export we did not do in our local machine. But export, what does export can extract your data from HDFS to RDBMS, just a vice versa. Frankly, I have never performed practically this. Okay, but I'll tell you this. What export can do. This is one option I believe Hadoop Scoop has given you, but not frequently we're using. Frequently we're using this import option. Then fourth is eval. If I want to do any evaluation from HDFS to RDBMS, from uh, not HDFS, I should say local file system of Cloudera to RDBMS. So suppose you do not have any access of RDBMS, because when you started working with the Hadoop project, you are not a part of this team. You are not a part of this team. This is taken care by DBA, database administrator. So if DBA has not given you any access of this RDBMS, then how can you check? You cannot install this, but still from HDFS you can access it. From local file system of your cluster you can access it. So that's what eval provides me. Now there are 2 more options. Options file, options file. Then options file is for not writing the connection always. I think this part we'll see when we do practical. Okay, just hold till then. Maybe tomorrow we'll get a chance to see this. So options file is just one query optimization, I'll say. Okay, where I'm not writing much line in the code. I can refer one file, and that file is my options file. Then other two are miscellaneous tool, guys. List databases, list down databases available in RDBMS, and list tables. So these are 7 arguments, basic 7 arguments. And in a scoop, we are going to see roughly 22 query. 7 to 8 queries are basic query, and rest all are advanced query. Okay, how can this extract records which you only want according to your requirement? Okay, according to the application. Now, check this system setup argument part is done, and I was about to mention one more thing. Our Cloudera is all there with you guys. Okay, so do one thing today. Please create your account. I think some of you have received some of the notification from, I think Arfa has created. Other people can also go to this site and let me open it actually. So this is the LMS site, guys. Now this is what I was talking about. Up, excuse me. So go to this login. Excuse me. Click on this. Since I've already logged in, I'll log out from there. Create an account here. Click on this login of this URL, and I will just wait. Yeah. So if you click on this login, click on this sign up, and you can give your email, you can give a you can give a password and sign up. Once the sign up is done, you'll receive your credentials. And if I use my mail ID, so please connect with the support post. Okay, this is logged in, and I'll go there. I'll see my some assigned videos. So you can watch these things right from here. Let's say I want to see the module number 18. Descriptions will be read what this module is. This is mainly important for counter is important for. So create this account today, okay? And credentials will be given to you within a week, so you can start checking this. I'll stop giving you things in Google Drive because I understand it takes time for me also to convert whole videos and over the network you download from there. We'll use this approach. So Scoop Practical will start from tomorrow, not starting today, because I want you guys to check all this communication. Once this is set, this main thing is set, then we'll start it. So see you tomorrow.